So in this little lesson, I want you to understand what is meant by induced charge separation, because it will explain some of the electrical phenomena we've already been discussing that you've probably already seen. And it applies to both conductors and insulators. And I've already made some comments about conductors that are pertinent. So for conductors, we consider the charges, and I said they are free to move around. Well, they're really electrons. Okay, electrons are the actual physical entities that are moving. But the key thing is that they're free to move in the material. They're not locked in place. So I'm going to look at various stages here then of our charged graphite-coated styrofoam sphere, which is what I'm using experimentally. In the first stage, we have this neutral conductor, and I show the presence of positive and negative charges. So in the second stage, we bring our charged rod, negatively charged in this case, close, and we know that it tugs on positive charges and pushes away negative charges. So really what's happening, well, I shouldn't say really what's happening, but the next level of accuracy, I believe, is to state that it pushes on the electrons in the clouds around the atoms and can literally move them off one atom to another. And so we have this situation happening here. So the object is still neutral, but the charges are separated. That's why it is called induced charge separation. There's a charge separation that's induced by this. It's not directly forced. It's done a little bit indirectly through what we could say a field force. And that results in the positives being attracted toward, but then at the same time, the same amount of charge, these are elementary charges, and the negatives are being, there's a force on the net from the negatives, this interaction between the rod and the negatives, in the opposite direction. However, this latter one we refer to is the smaller force. And the reason for that, as you probably can maybe tell right away, is because they are further away than these charges. These charges are closer, the force is stronger, further away, weaker. There you go. If you add the forces like vectors, guess what we get? You guessed it, we get a net force, which causes the object to move toward the charge rod. And there it is. During that whole process, the sphere never attained any charge. Okay. So, kind of in summary of this, the moving charges are electrons, not protons. And the electrons, with very little force, transfer between the atoms. Then the protons are really shielded by the electron clouds. But again, all that we don't even have to worry about. We can just consider these charges as entities that are free to move, both the negatives and the positives. And of course, when negative moves, it leaves a positive in its wake. And yet, functionally, they just act like equal but opposite charges, free to move around. So now, let's consider insulators and the big difference between insulators and conductors for our purposes of seeing how charges respond to external charged objects is that the charges, that are really electrons, are locked in place instead of free to move around in the atoms. So here we have an apple. Now, my apple is my representative insulating object. It's really not a very good insulator. Electricity actually will conduct through an apple, but it was such a shiny, beautiful little graphic that I couldn't help but use it. So anyway, illustrates the point nevertheless. So I'm going to pick a region here. This little dot represents the location of a particular atom. No, it's not really beryllium, but I'm showing 4 protons, 4 pluses in the nucleus, just for illustrative purposes. And statistically, the electrons that are part of the atom, with their probability distributions, are evenly distributed spatially in that region. And so I can draw them in here, and you'll see that on the average they're about just as many on the right side as on the left side, or just as often on the right as on the left. You get the point. Now, what happens when I bring in a charged object? Well, here's what happens. We induce a charge separation. That's what is being shown by the line of positive and negative, but it's not like negatives exist here and positives exist here. It's not quite like that. This is the net effect of it. Now, how does this happen? Because we've already said the electrons are held in place or locked in place. They're not free to move from one atom to the other. Well, it's really not too hard to understand. So let's take a look. So we have the apple again with the charged rod close by, inducing this charge separation, which is really the net or total effect of what's happening to all the atoms in the apple that are being affected by the field produced by this rod. Oops, did I just say field? Guess you don't know what that is. But the forces from this rod that's charged on the atoms in the apple. So let's look at both sides of this. We're going to have a location on either half, the closer and further away. And I'm going to divide the atom right down the middle. And so what we see is, because of the rod's charge, it puts a pressure or force on the electron cloud. And what it causes the electron cloud to do is basically shift the electron positions over to the left. So statistically, they're more often going to be on the left side than the right side, which results, for an individual atom, in charge asymmetry, namely positive on the right, negative on the left. Now, that's being done to all the atoms in the apple. So a corresponding atom on the other side, it'll happen there as well. But the effect will be a little less pronounced. Nevertheless, it's still a little effect on all the atoms. But the really main point is not that it's a smaller positive and negative side here, smaller font. Overall, it's neutral, but every atom has this slight shifting of the electron cloud. And if you do that to every atom, the net effect on the whole object is to be able to model it as a positive side on the right and a negative side on the left. So that works pretty well as a model. So we have on the right side F plus from the force from the positive charges, and also force from the negative charges. And you'll notice, because for every atom, positive side is closer to the charged object than the negative side, what's the larger force going to be? The force from the positive charges, because they're closer. So hopefully that makes pretty good sense. As a result of that, we get the following to happen. Again, assuming the apple is a neutral object, we have a net force when we bring the charged rod close to it. So when you take this force and subtract this other force off, you still have a net force left. Therefore, neutral objects actually can be attracted and are attracted to charged objects. So in that way, you can take a charged rod, you can put a comb through your hair perhaps, and put it real close to little bits of paper, like Kleenex paper or something, and you'll notice those insulating objects that are not charged being drawn up to the comb. So that will about do it for this little lesson. I hope you enjoyed the little bit of learning that took place.